Okay, so I'm going to make this little video to see if I can attempt to explain to people why it is that prefabricated bus bars will not work as good as homemade all copper bus bars. Now, first of all, let's talk about what it is that an electric motor or electronics in general need to produce power. And that's two things, voltage and current. Now, in this situation, we're talking about current flow because it's a battery. So the more current flow, and current flow is defined as the movement of electrons through a conductive material, okay, like this copper. All right, now, depending on how thick this copper is, how wide it is, its total mass is how many electrons can flow down this piece of copper, right? Now, copper is highly conductive, so it's really good as far as the movement of electrons, and the thicker it is, the more electrons that can flow. Same thing with this piece of nickel. Although it's not as conductive as copper, electrons can still flow rather freely down it. Now, when building batteries, we are connecting the cells using either nickel or copper, all right? In some batteries, it is just straight nickel only. Sometimes there's just single pieces of nickel like this. Smaller, as far as the width, they're thinner. Some are wider, and some are thicker. All right, like some are like 0.1 millimeter thick, some are 0.2 millimeter thick, some are 0.15 millimeter thick. The thicker, the better, as we said. Okay. Now, at the same time, when we're making these connections to our batteries, we are welding the copper or the nickel to the cell. Now, the thicker the copper or the thicker the nickel is, the harder that it is to weld it to a cell. So, for optimum current flow, sometimes we're using copper that's as thick as 0.2 millimeter or 0.3 millimeter thick. So that's pretty thick, and it takes a lot of power to weld through 0.3 millimeter copper. At the same time, we're doing what we call the nickel sandwich technique, and that is using a piece of nickel and copper because it's easier to get a better weld with nickel on top of copper instead of just copper alone. Okay, copper is real good to conduct electricity, but it's harder to weld by itself. So, that being said, when you have to add this nickel strip on top of this copper, that is making it even thicker, meaning it's going to take even more power to weld it. All right. Now, most people don't have high power welders. They're very expensive. So the average welder isn't, like I said, high power. It's moderate power. And the average welder is only capable of welding just, regular nickel like this. That is mostly 0.1 or 0.15 millimeter thick. Okay, so most welders can weld that. All right, so prefab bus bars, in order for them to conduct a lot of current, they have to be pretty thick, right? But again, average welder can't weld that. So they have cutouts, meaning there are holes in the copper, basically like this nickel, these openings, cutouts, where they have a piece of nickel underneath of the, well, actually it's laser welded to the copper, but because there's an opening in the copper, that makes it so any welder is capable of welding that prefab bus bar to a cell, because it doesn't have to weld through the actual copper. There's an opening in it. It only has to weld through the nickel, okay? So that makes it great. Anybody can weld a prefab bus bar. And one thing about prefab bus bars, they look great. They make your build look really professional, but they can't handle as much current flow as a solid piece of copper, because of that cutout and that nickel that's in there. The nickel is not as thick as the copper, so obviously it can't handle as much current flow, okay? So if you got a really thick piece of copper like 0.3, and then you have a cutout where you have 0.1 millimeter nickel there, when those electrons flow down that copper, they're moving at a high rate of speed. They can flow freely. There's little or no resistance. But as soon as that current has to flow from the copper to the nickel, then all of a sudden it has to slow way down, because this nickel strip is not as conductive as this thick piece of copper. All right, so there's going to be some resistance there. So that means if you got a copper bus bar and it has several cutouts where there are several openings with nickel on the back so it can be welded to the cell, that means that entire bus bar is going to have a lot of resistance in it because of all of those inserts, those nickel inserts, right? So if you look at prefab bus bars, they give a current rating for them, and sometimes it'll be like, all right, it'll be a bus bar, it'll be 0.2 millimeter thick copper with nickel inserts, and they'll say that bus bar is capable of conducting 150 amps, right? And it's only 150 amps because of those nickel inserts. Now, if it were the solid piece of copper, 0.2 millimeter thick, the difference in the amount of current flow is massive. That solid piece of copper can probably conduct 2 to 3 times the amount of current flow. All right, so now we're talking about a bus bar that can now be able to conduct 500-600 amps instead of the 150 to 200 amps, okay? So there's a big difference in the amount of current flow, which is why I only use straight copper, and it's copper nickel sandwich, because the copper is in between the nickel and you welding it to the cell. So not only are you getting the benefit of that solid piece of copper, but you're also getting the conductivity of however much this piece of nickel strip can carry as well, because it is adding to the total metal material mass of the copper. It's not being subtracted. Like with cutouts, you're losing copper and it's being replaced with nickel. When it's copper nickel sandwich, you're adding to it. So you're not taking away from this copper mass, you're increasing it by adding nickel to it. So again, you're getting the current flow that this solid piece of copper can handle, plus this. So again, the difference between a prefab and this is huge. So in that case, that is why some batteries are going to be able to produce a lot more current than others, and that all depends on how much the actual cells and how many cells in that pack can produce. So, you might have a 10p pack with, these are JP40 cells. Now, I'm making up a number, not exactly what they can produce, but let's just say 10 of these cells, they can all produce 100 amps each. So 10 of them in parallel, that should be 1,000 amps, right? That means those 10 cells have the capability of producing 1,000 amps. But that doesn't mean because they're in parallel, connected together with a nickel strip like this, that you're going to get 1,000 amps, obviously, because this nickel can't conduct 1,000 amps. There's no way 1,000 amps can pass through this. But if you had a copper bus bar that was thick enough and wide enough to pass 1,000 amps, then you're going to get the full capability of those cells. All right. So there's a lot of factors at the end of the day of how much a pack can truly make, and it's based on the particular cells being used, how many of them, and then how that pack is constructed. Now, you can have a pack with great cells, with great bus bars, but at the end of your pack, when you're tapping into it to get that power from the pack, you have a power wire that's inadequate. So this 8-gauge power wire, if it can only conduct, and then let's just say roughly, making up not the exact number, let's say it can only conduct 100 amps. 100 amps is the most amps that can pass through this wire. No matter if this pack can produce 1,000 amps, if this 8-gauge wire can only conduct 100 amps, then that's all you're going to get at the end of it, regardless. All right. Same time, the connectors you use. Now, let's just say you got a wire that can handle that 1,000 amps or whatever. And even though this can't handle 1,000 amps, let's say it could. All right, now we're talking about the connector. This is a QS10. This QS10 can only handle 400 amps, right? So you put this 400 amp QS10 on there. Now you got 1,000 amp pack with 1,000 amp power wires, but you're still not going to get 1,000 amps at the end of this connector, because this connector can only pass 400 amps. So that means everything has to be capable of that 1,000 amps, right? Now, the other thing that can affect your battery is the BMS, because the current goes through the BMS. So if your BMS isn't capable of passing 1,000 amps, then you still can't get 1,000 amps. And that's why some people bypass the BMS, because they got a pack that's built capable to produce 1,000 amps. Far as the bus bars, far as the power wire, far as the connector. But the BMS is limiting it to whatever that BMS rating is. All right. So that's why somebody would bypass. They want the full potential of this battery. So, like I said, there's a lot of things that play a role, and you have to keep all of that in mind. And whatever point of your system is limiting the current flow is what we call a bottleneck. These bottlenecks are going to cause voltage sag, all right? So whatever is limiting that current, there's going to be a voltage drop there. You're not going to be getting the full potential. Voltage is actually the potential difference. So if there's voltage sag, your voltage is going to drop, all right? So another thing I see people do, especially on Surons, they buy a great pack, a pack that can, let's say, a pack that can produce 500 amps. They put it on their Suron. They even have, the battery is made well right gauge wires, right connectors, or even the right number of connectors, because sometimes you need dual connectors. Like if you would need 2 of these QS10s to make 800 amps. So you got 2 sets of leads to make those 800 amps, right? Now, they take that and put it on a Ciron and then connect it to the factory wire harness that's on their Ciron. And that factory wire harness has a 150 amp circuit breaker. So now they're attempting to run their controller and everything else off that battery pack that's going through a 150 amp circuit breaker. Bam, that's another bottleneck. You don't do that. You went out and got a great pack. You got everything else right. You got a high power controller that is capable of 400 DC line amps, but it's got you got a 150 amp circuit breaker in line. All right. All of this makes a difference at the end of the day. So when you see guys out here and they are struggling to get to the same speed as other guys that got the same stuff, and they say, man, I'm on 72 volts, I got the same motor as you, the same controller, but I'm not, my bike isn't accelerating as fast or whatever. I mean, it could be any of those things that could be limiting and holding you back. So the top guys, the guys that know how to get the speed, they are doing what's necessary to get the maximum power and, with the best efficiency. Their system is optimized. So that's what I want you guys to understand. So when you got battery makers that are making handmade bus bars, you got to understand that these guys are going to charge a whole lot more to make and build a pack for you, because it takes a whole lot more time. You buy prefabricated bus bars, you buy them, they're ready to go. All you got to do is weld them. Bam, 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 bam. They look good and they're great, but bam, they only can do 150 amps. But the guy that's peeling off this 0.3 millimeter copper and cutting it to fit, and it's a lot more work, so it's going to cost more. And the bottom line with all this stuff is, as it always been, you got to pay to play. All right, that's the little lesson for the day. It's all about current flow. This is electronics, e-bikes. If we were riding gas petrol bikes, petrol vehicles, then it's about airflow. That's why guys, when the first thing they do, they modify their car, they put a big exhaust on it so more air can flow. Not just the exhaust, they put a bigger intake so more air can go through the intake. It's airflow. That's petrol. This is electrical. It's current flow. Current flow at the end of the day. It's all about current flow. Peace.